All right, welcome to this rapid fire explainer. We are going to get you totally prepped and ready for that private pilot license ground exam. If you've spent any time at all in the left seat of a training aircraft, you already know that airplanes kind of have a mind of their own, especially the second you push that throttle full forward. So today, we're demystifying the actual physics behind exactly why your aircraft desperately wants to veer off the center line.
But hey, before we get too deep in the weeds, I've got a quick question for you to ease those pre-exam jitters. Why do student pilots make terrible dancers? Well, it's because they have two left feet and a remarkably strong left-turning tendency. Okay, dad jokes aside, that left-turning tendency is a massive chunk of your PPL ground exam. And honestly, mastering the why behind it, that's going to make you a much better and definitely safer pilot. So the quote-unquote torque, or left-turning tendency of an airplane, is actually a combination of four totally distinct aerodynamic elements that you will be tested on. We've got torque reaction from the engine and propeller, the corkscrewing effect of the slipstream, the gyroscopic action of the propeller, and asymmetric loading, which most of us just call P-factor. For this explainer, we're going to zero right in on those first two, torque and the corkscrew effect. Okay, let's jump straight into Section 1, torque reaction and Newton's third law.
You absolutely need to memorize this definition because it is literally the fundamental rule governing torque reaction in your aircraft. Sir Isaac Newton's third law of physics simply states, for every action, there's an equal and opposite reaction. Sounds super simple, right? But when you apply that to a giant spinning piece of metal attached to a high horsepower engine at the very front of your airplane, well, this basic law of physics suddenly becomes a very real force that you have to wrestle with in the cockpit. To picture exactly what Newton was talking about, imagine you're sitting in the pilot's seat of a standard US-built aircraft. Your internal engine parts and your propeller are revolving clockwise. That right there is your action. The reaction, it's an equal force trying to violently rotate the entire aircraft in the exact opposite direction, counterclockwise. So your airframe inherently wants to roll to the left right around its longitudinal axis.
Now you're probably thinking to yourself, wait a second, when I'm just flying straight and level at cruise speed, I am not constantly fighting a left roll. And you know, you're totally right. When you're airborne at cruising speed, the aircraft manufacturers have already done the hard work and compensated for this left rolling torque. Modern aircraft often just have permanent engine offsets built right into the mount itself. Older planes might use specialized wing rigging, so the wing getting pushed down naturally generates slightly more lift. And of course, you've got aileron trim tabs for fine-tuning. The big takeaway here is that these factory compensations are optimized for cruising speed, because, well, that's where the airplane spends most of its life.
But what happens when you aren't at cruising speed? Let's look at Section 2, ground yaw and the takeoff roll physics.
The physics of this situation completely flip the second your wheels touch the runway. During a high-power takeoff roll, an extra turning moment around the vertical axis is created by that exact same torque reaction we just talked about. Think of it like a chain reaction. Torque forces the left side of the aircraft down, right? Because of that downward slam, way more weight is placed directly onto your left main landing gear. That extra weight creates significantly more ground friction, or drag, on that left tire compared to the right one. And when the left side drags, the aircraft experiences a sharp yawing moment that aggressively pulls your nose to the left.
So, a massive point to remember for your ground exam is these four specific variables that directly dictate the magnitude of that left yaw. Because look, not all planes yaw equally. The size and horsepower of the power plant matter a ton. A massive engine twists harder. The size of the propeller plus your RPM changes the rotational mass. The overall size and weight of the aircraft dictate how easily the whole airframe gets bullied around by these forces. And finally, the environment. A clean paved runway is going to grab that left tire so much differently than a slick, wet grass strip.
And because of all these crazy variables, there is no magic factory setting that can perfectly fix ground yaw. To counteract it on the runway, it is 100% up to you as the pilot in command to step on that right rudder or adjust your rudder trim. Remember the golden rule. Anytime you push that throttle forward, your right foot better be waking up and ready to work.
Moving right along to our next core topic, Section 3, the corkscrew effect, which is also known as the spiraling slipstream.
To really wrap our heads around this one, we kind of have to visualize the invisible air wrapping around the aircraft. The high-speed rotation of your prop basically turns the slipstream of air into a corkscrew. Imagine you're at high power and low forward speed, like during a takeoff or a power on stall. That slipstream becomes this tightly coiled, super compact spiral of air. It travels backward, wraps around the fuselage, and then absolutely smacks into the left side of your vertical tail fin. When it hits the fin, it shoves the tail to the right, which acts exactly like a seesaw, forcing your nose to yaw left around the vertical axis.
Now, a big exam takeaway here is that the strength of this force is entirely dependent on your speed. As your forward speed increases, that tight corkscrew of air actually elongates. Actually, think of it like taking a coiled spring and stretching it out. Because it's stretched, the angle that the air hits the tail totally changes, making it way less effective at pushing against your vertical fin. So low speed and high power, maximum corkscrew effect. High speed, minimal corkscrew effect.
Here is a super fun twist they absolutely love to test you on. The corkscrew flow doesn't just yaw the plane, it also causes a rolling moment around the longitudinal axis. But listen closely to this. The rolling moment from the corkscrew flow is to the right. But remember what we just learned? The rolling moment caused by torque reaction is to the left. Which means, crazy enough, up in the air, these two distinct aerodynamic forces can actually fight and counteract each other.
But hey, don't let that lull you into a false sense of security where you think the plane just flies itself. Ultimately, because aerodynamic forces are constantly moving target based on your airspeed, your engine RPM, and your angle of attack, the most prominent force shifts all the time. It is always, always your responsibility to apply the proper corrective action. Like the old instructors always say, just fly the airplane. Use your ailerons and your rudder to counteract whatever force is winning at that exact second to maintain coordinated flight.
So as you're sitting there studying, visualize that next takeoff roll. Ask yourself, when I shove that throttle forward, which of these forces is going to be the most prominent in my cockpit, and exactly how much right rudder am I going to need? Understanding the why behind the physics is going to make the how of flying feel so much more intuitive. Good luck on that PPL ground exam. And hey, if this explainer helped clear up the left-turning tendency for you, please smash that like button and subscribe to our channel for more ground school explainers. We will see you up in the skies.